Well, good evening and welcome to Monday Night Calculus. Your questions are answers. This is, I guess, I don't even remember what episode number we're on here, but it's our first one of 2022, and I'm super excited to have you here. My name is Curtis Brown. I will be hosting this evening, and I'm joined by Steve Kokoska and Tom Dick. As always, guys, it's a pleasure to have you guys working with us here, and thank you for sharing your knowledge and time with us. I've got a few housekeeping things that I'm going to take care of, guys, before I let you take it off. First of all, like I said, this is our first session of the new year, and I'm really excited for that. And we have a couple of things. We're going to change some stuff up. As you notice, we are starting at 8 p.m. Eastern time instead of 7 p.m. as we had been before. So that's an important thing to note. We'll be carrying that out through the rest of the spring. Secondly, and maybe more importantly, I'm going to ask you guys to check in on the chat. And here's the reason. I'd love to know where you're watching from and whether or not you're a student or a teacher. The reason is tonight and actually every subsequent evening, the rest of this spring, we're actually going to be doing a little bit of a giveaway at the end of the live sessions, which is going to be really cool. It's a super exciting giveaway. What we're going to be drawing for is an opportunity to have Steve and or Tom teach a 1-hour session with your class remotely. We won't be sending them into your school there, but we will figure out a way for you to have them teach your class remotely. And so what we want to do is have you guys interact in the chat, and from the folks who are interacting with us on the chat, we will then give out that opportunity. We'll select someone from the chat at random, or maybe based upon interaction. We'll just see how Allison chooses to do that. But the idea is going to be that we're going to do this based on the chat box. So that's going to be really cool. Super excited to begin to host those kinds of sessions as well. And so, Steve, I'm going to let you take it over.
All right.
From here.
Well, thank you very much, Curtis. It's delightful to be with you again. And thank you, Allison. We never see you, but thanks for all the work you do in the background. Tom, good to see you. There were some great questions in the Facebook group as the new year started. And this is kind of a cool one to start out with, I think. This is from Jen. Help me with this, Curtis. Is it Spurky, do you think? I don't think it's Sparky, but I'm going to go with Spurky, maybe with the E on the end.
Yeah.
Yeah, okay.
That's right.
And it was a very simple question. She actually had a hand-drawn graph with this. She said, what happens if F prime flatlines at 0 for a while? Now I'm going to have you'll allow me a little literary license here to interpret that. But when I read that, Curtis, I immediately thought of this question from 2018, and we'll get to answer this question from Jen eventually. But I believe that part of this question answers and addresses this. This question in 2018 actually generated a little bit of controversy here, especially with part D, and I know Tom will help me with this a little bit. But here's how it goes. This is a cool one. So this graph given is the graph of a continuous function G, and it turns out that this is the derivative of a function F. I'm trying a little something new tonight, Curtis, for the way I write here, so hope I don't jump around a lot. So we know that G is equal to F prime. And I'm going to add a little bit more in while I'm here. You can see that this graph of G is made up of some straight line segments. You can see that G is kind of, flat line. It has slope 0 in several places. But there's also a piece of a parabola on the right end there. And I'll just write that as 2 times x. I think it's 2 times x minus 4 quantity squared. Okay, so we know that G is equal to F prime. And we have 4 questions here. If we know that F of 1 is equal to 3, what's the value of F of minus 5? We want to evaluate this definite integral if we can. Very typical sort of an AP question here. On what open intervals in part C is the graph of F both increasing and concave up? And then D is the real interesting one for me here. I'm going to try to make an argument here, and you may discussed this a little bit with me, Curtis. It says, find the x coordinate of each point of inflection of the graph of f. So let's see what we can do here. In part A, we want to find f of -5. And I think the way to attack this, to start this one, is to think about the fundamental theorem of calculus. So I'm going to add a little bit over here in my own words. This is really just the fundamental theorem of calculus used appropriately. Remember that this works for any antiderivative of g, and we know that little f is 1. So that's just an application of the fundamental theorem of calculus. And then what I did in the next step is I actually just solved this expression for f of -5. Now, I kind of like the way that this works out because this is the smaller of the bound here. And now what I do in order to find that definite integral, remember, I don't have an explicit expression for g except where that parabola is over there on the right-hand side. And this is very typical of these AP exam questions too. We have to find this answer geometrically using an area argument. So if I sneak back up here, we've got to go from -5 to 1. Let's see if I can get some of this in here. So let's see, from -5 to -2, okay, I've got a nice square in there. I know the area would be 9, 3 times 3, but this region is below the x-axis. So I have to attach a negative sign to that. This region right in here is the area of a triangle, but again, below the x-axis, so that computation would be negative. From -1 to 0, the graph of g is right on the x-axis, so there's no area. And then from 0 to 1, we have another triangle in there, and that would contribute a positive value to that definite integral. So I think I did all of that in here. You'll notice in my expression inside those big parentheses, I don't have the 0 in there. But there are the expressions for area with the appropriate sign attached. I did a little bit of a simplification there, and I ended up, I think, with a 25/2. Now, I'm not going to talk about, if it's okay with you, Curtis, I'm not going to talk about the distribution of points here. That's for another evening, how points are awarded. I'm more interested, I think, in the ideas, the conceptual, the calculus ideas here. So that's part A. Now, I've just reproduced the graph here on my page, just in case I wanted to look at that. Part B, I think, was almost anticlimactic here. We want to find the integral from 1 to 6 of g of x. And the first step here, for me, is just a property of integrals. And just as sort of an aside here, this is kind of a constant, not theme, that's not the right idea, but a constant testing technique, I think, on the AP exam. These questions frequently involve lots of different concepts. So even in this one part, the student has to be aware and make use of this idea of this property of integrals. So definite integral 1 to 3 plus definite integral 3 to 6. This definite integral, we're going to use an area argument. What is that, 1 to 3 again? Okay, that's not so bad. That's right in here. That's a square again. But from 3 to 6, let's see, we know the equation of that parabola. And so from here to here, the student has to find an antiderivative. Now, if I've skipped just a little bit of a step here, that's a pretty easy, I think, U substitution. And I often get asked, well, does the student have to explicitly specify that U substitution on the exam? And the answer is probably not, but I would, just in case there's any chance of partial credit in the event that the student made a mistake later on. But that's a pretty easy U substitution. Plug in the upper bound, plug in the lower bound, do a little subtraction and simplification, and I think I got a value of 10. That's kind of cool. All right, where's the graph of f increasing and concave up? Well, okay, I'm going to add a little bit off to the side here. My printing is doing okay this evening. I just want to remind you here that g is equal to f prime. So let's see. Let's see, where would f be increasing? Well, let's see, that would be where g is positive. So I got to go back up to the graph here. Let's see, where does that happen? Well, that happens all the way over here, doesn't it? 0 to 6, but wait a minute. Where is f concave up? Well, that would be where the derivative is increasing. So let's see, where does that happen? Here, and 4 to 6. So by looking at that graph, I can see that f is increasing and concave up on the intervals, on the open intervals, 0 to 1 and 4 to 6. Cool. Now for the interesting part here. Where does the graph of f have a point of inflection? Well, let's see here. I got to think about this a little bit. Where does the graph of f have a point of inflection? Well, that would be where its derivative changes from increasing to decreasing or vice versa. So I have a graph of g on this graph right here. And I have another graph of f, which I'll talk about in a minute. But let's just take a look at g for a second. Are there any places on this graph where g changes from increasing to decreasing or vice versa? Well, there's only one. And it's right here at x equals 4. It's decreasing down there, and then it's increasing. And darn it, that's the only point of inflection. Now, here's sort of the controversy. What the heck is going on here with these flat lines? What's going on here? Well, let's just take a look over at this flat line right here, where the derivative, where the derivative of f, g, is constant at -3. Well, what would that say about f double prime? Well, that would be the derivative of g. That would be 0. So what does that mean here? Well, in the context of this problem, I believe it means that the graph of f actually has no concavity over that region. And I'm going to try to justify that to you by looking at this graph of f over that interval -5 to -2. I believe that the graph of f has no concavity there. And the reason is because if I pick some point on that graph, can you draw a tangent line to the graph at that point so that in some neighborhood, the graph of f is always above the tangent line or always below the tangent line? And the answer is you can't, because the tangent line, darn it, is right on the graph of f. So there's no concavity, and therefore there is no change in concavity here. There is no change in concavity here. Look at the graph of f. There's no concavity there. There is no change in concavity here. There's no change in concavity here. But son of a gun, when we get over here to x equals 4, you can kind of see that the graph was concave down, and now the graph of f is concave up. There is indeed a point of inflection right in there. Now that's a really cool problem, and again, that's the answer. That's the way it was graded. Tom helped me on this a little bit. I think we made some exceptions and awarded a point for some students who made an argument about what was going on between 1 and 3, or between between -1 and 0. I don't recall exactly what that argument was. It was a while ago, but we were very sensitive to what students responded there, because this was a tough problem.
Yes, and I think there was probably amongst the exam writers, there was an oath taken never again. I mean, I think the nuance here is your graph of f. Yes. One could take a look at it and say, well, there's clearly a change in concavity between -5 and 3, because I can see it's concave.
It looks like it's concave up like this, right?
Right.
Yeah.
Let's see, did I misspeak here? No, I think, let's see. Well, it wasn't the change in concavity. The issue is that comes up would be, is there
is there an inflection point, for example, between 1 and 3? I recall that sort of discussion.
Between 1 and 3 certainly makes the most sense to me, and because you do have that concave up section between 0 and 1, right? And you have the concave down section between 3 and 4,
for example.
Right.
Yeah.
Right.
So it's clearly
what is
there's
that
been a
linear piece really doing? Yeah.
Yeah. But I think the strict definition of a point of inflection, what we don't think of it has to be a point. It has to be a
Right.
point where that concavity changes, and it can't have a change over an interval.
Or an interval
like
of inflection.
This, so.
Ooh, that's a strange term, interval of inflection.
Yeah, we don't
yeah, in a sense, you'd have to come up with a new term for something like this,
right.
and it wasn't intended to get into that kind of a nuance.
Yeah.
So they tried to be, I think, I think they tried to reward students who were arguing in good faith about what they were seeing, and as long as they didn't say something that was just outright incorrect. Yep. But if they, this issue of, look, I can tell that the concavity's changed, there's got to be a point of inflection. Well, it's the whole point, pun intended, is the emphasis on point.
Let's see what you did there.
Yep. Very cool.
So, yeah, it was a tricky one to grade for sure. So.
And I think you're right. I think it will be very unlikely that we see a problem with this. But having said that, here's an interesting one from Brendan Hughes. Now, let me just comment a little bit on the wording here. I apologize for this, Curtis. I'm not exactly sure where Brendan got this problem. But if I were writing this, I would word things just a little bit differently. This is a little cryptic in what some of these questions are asking for, but I think we can decipher everything. It says, look, let g of x be defined to be the integral from a to x of f of t dt, and f is given in this graph below here. It's made up of several linear pieces. And you'll notice here, thinking ahead, looking ahead, we know that the derivative of g is f, and son of a gun, there is another part here where there's a flat line here in this derivative. So given that we just discussed this one, it might make this a little bit easier. Just find the x values of g regarding each of the following conditions. Okay, now I think we can zip through this because we're really good at this. This is a kind of a neat review to lead us into the new year here. Where are the relative minimums of g? Well, we know that g prime of x is equal to f of x, and we know that, of course, by the fundamental theorem of calculus, okay? And so we know we have a relative minimum at x equal 8 because there, g prime equal to f changes from negative to positive. So you can kind of feel, you can kind of see this function g decreasing and then increasing. So we know we have a relative minimum at x equal 8. And similarly, we know we have a relative maximum at x equals 6 because we can see from the graph, we can feel this graph of g increasing up to 6 and then decreasing. We know we have a relative maximum there. Where is the graph of g concave up? Well, let's see. It would be concave up where f is increasing. Well, let's see. Where does that happen? Let's see where its derivative, f is increasing. Well, that happens 0 to 2. And let's see, is it 7 to 9? It would be concave down. Let's see where f is decreasing, where its derivative is decreasing. And so that would be from 3 to 7. And I guess I was going to ask this as a question, but maybe given what we've discussed already here, seems like there's a missing interval in here between C and D. I mean, what happened with that interval 2 to 3? What's going on in there? Well, all right. A little bit of a hint. There's that flat line up there. And so my argument is that once again, there is no concavity there associated with this function g. There's no concavity associated with g there. All right, so this is kind of backtracking a little bit about where is g increasing, where's it decreasing, is there a point of inflection? Well, let's see. Where's it increasing? Well, wherever f is positive. And you remember here, Curtis, we've talked about this frequently. I used to close intervals. So let's see, it's 0 to 6, and then 8 to 9. It is decreasing where f is negative, 6 to 8. So let's see, is there a point of inflection here? Is there a point of inflection? Yes, where the derivative changes from increasing to decreasing or vice versa. Good reinforcement for what we just did a minute ago. That occurs at x equals 7. So you know what? Those are good basic questions that every student should be able to answer from a graph of the derivative here going into the exam as you get ready for this in May. And here's a couple of other nice ones. It says if g of 2 is equal to 1, what's the maximum value of g on the interval 2 to 9? And Curtis, I'm going to ask a couple of questions that might go in the chat here for this, okay?
Sounds like a plan. We'll post them in the chat.
All right. I'm going to skip a little bit here because I want a couple of answers in the chat. I believe that the maximum value of g occurs at 6.
Okay.
And I'm going to sneak back up here, and I'm just going to let you stare at that for a minute, at that graph.
Okay.
Stare at that graph. I think you would be willing. Well, we already know that there's a relative maximum there.
Sure.
My argument is that that is indeed the absolute maximum value of this function g. Okay, so hold that aside. Now I'm going to try to find this value, g of 6. I'm going to use a property of definite integrals here. I'm going to split this up a to 6 from a to 2 and 2 to 6. That's a property of definite integrals. This expression right here is really just g of 2, and that's 1. And this expression right here, I'm going to compute by going back up to the graph and once again using an area argument. So I believe that the absolute maximum value of this function g over that interval, 2 to 9, is 17 halves.
Okay.
I'm going to put for the chat, I want to know a couple of things here. First of all, why don't I have to check those endpoints, g of 9 and g of 2? Why don't I have to look at those? And it also seems like, well, if I look at this graph, and remember that in this kind of prescriptive way of finding an absolute maximum, we find the places where we find the critical values, and x equal 8 is a critical value. And so why don't I have to look at x equal 8? So there's lots of questions in there. I think the basic one is, why don't I have to look, why can I eliminate those 3 values? And, you know, that's a common question that I get about the exam. You know, sometimes students can look at these problems and say, oh, well, you know, I don't have to look at these 2 values. I know right away that the absolute maximum must be a g of 6. Well, that's fine, but there must be some sort of statement here, some sort of reason or justification for eliminating some of these other values.
Okay.
So maybe
I'd like to know what folks will put in the chat based on why can we eliminate some or all of those values.
This is probably the easiest one to answer. Why can I eliminate g of 8? But
can you scroll back up for us so we can see that g of 8, g of a, and g of 2?
Yep.
Because I think that's important. We'd be able to look at this graphically to be able to answer those questions.
Sure.
Why don't we have to check 8? 8 is pretty reasonable, right? Since you've asked the question about it being a maximum.
Okay.
The derivative, you've given me the graph of the derivative. So if f is negative on the left-hand side, or the left-hand side of 8, and positive on the right-hand side of 8, which indicates that we've got a minimum there, not a maximum.
So you don't have to look there. Very good.
Right. So we don't have to look at 8.
Very good.
That makes good sense.
So one might be able to make an argument as to why you don't have to look at 2 and why you don't have to look at 9. And here's another extra credit problem for the chat window too. Tom, help me on this one, but I believe, given this information here in F, can you actually solve for the value of A? Is that true, Tom?
Well, I believe you can, because G is defined as this definite integral function,
right,
from A to X. And here you're given the value of the definite integral from A to 2 is 1.
Right.
So I think looking at that graph of F, you could figure out the value of A. Now, it turns out to not be a very nice value, because I think you end up getting kind of a little quadratic equation that you have to solve, and it actually isn't one that has nice roots. It'll have a square root in it. No. So, Steve and Curtis, I'm going to kind of jump in here, if it's okay.
Sure.
And say a little bit about, I just want to be kind of careful. I think everything you've said is just right on the money. But this, in terms of the exam, if you're asked to find an absolute maximum value or absolute minimum value on a closed interval,
yep,
you will be expected to address the endpoints.
Mm-hmm.
And I want to make a distinction. We've been talking about, well, you don't have to look at them. Well, yes, you do have to look at them, but you'll have to either argue why. The simplest way to handle them actually would be what's called the candidates test.
Yep.
And that's where you just go ahead and evaluate the function at the endpoints. And you compare those values with the ones at the relative extrema. And if they're bigger, they're keepers. If they're not, this would be for a maximum. What you guys have been talking about is you can make an argument about why you wouldn't even have to evaluate at the endpoints. In other words, you can rule them out, but you have to explicitly rule them out. You can't just ignore them.
Right.
So what I'm saying is you could look at it and say, well, it can't be 2 and it can't be 9, but you have to explain on your paper why it can't be 2 and why it can't be 9.
Right.
Oh, here's an interesting, so we've got some responses from Wanda. Burns has responded. So you can eliminate G of 8 because G decreases from 6 to 8. So you accumulate negative area. You can eliminate G of 9 because the negative area accumulated from 6 to 8 is larger than in magnitude, greater in magnitude than the positive area accumulated from 8 to 9. Okay.
Okay.
So we know that we're not any higher at that point.
Okay. Cool.
And then I'm going to go out on a limb here. I haven't seen anybody else post anything in the chat, so I'm just going to go for it.
Okay.
And you can tell me that I'm not right. That's totally acceptable. But I would argue that G of 2, is that the other one we're trying to eliminate?
Yes.
We're still increasing after we have seen 2, right? So the area, to use Wanda's language, the area accumulated is still positive to the right hand of 2. So I know that I'm still increasing in value on f of x at that point, in those points.
We know that G is increasing. Yeah, good. Very good. Okay. And as Tom said, boy, you better put that on your exam. All right. I got one.
Look, I've learned a little calculus through this year.
All right. There is a part G here that I think Tom's going to, are you going to try some technology after that, maybe, Tom? Just for a second or two?
Yes, I've got something I can show folks here.
So this is one extra part here. G says, suppose that h of x is defined by this integral expression. And notice that the upper bound now is a function of x, a linear function of x, but a function of x. It says find the x value where h has a relative minimum. Okay, so I'm going to do just a little bit here, leave a little bit for you to think about. I'm going to find h prime right here. Now I've skipped a couple of steps here. I am using the fundamental theorem of calculus, but also the chain rule. That 1/2 on the end is the derivative of that expression that is the upper bound. Now, where the heck is h going to have a relative minimum? Well, let's see. That would be where its derivative is 0 and where it changes, let's see, from negative to positive. So I've got to go back to the graph and I've got to think a little bit about this here. Where does that occur? Let's see, that occurs over here at x equal 8, where f changes from negative to positive. So that means that argument, where did it go? There it is. That argument right here must be equal to 8. And I solve that and get an x equals 6. That's a little bit of a different sort of a problem, but I like that. We frequently see questions like this, functions defined in terms of other functions that are given to us in the problem, graphically, tabularly. Nice question. All right, Tom, I'm going to let you do a little technology and then I'll come back for the cool problem. So I'll stop sharing here.
Okay.
There you are, sir.
Great. All right. And I'll look for some feedback from you all that I did this successfully. Let's see here. And let's see. Yeah, I'm going to give it a shot.
Okay.
See what we got. Is that
looks good?
Okay, let me get the calculator screen on there.
Yeah.
And so what we've got here is this is a TI-Nspire file that was created explicitly to kind of deal with derivative functions like the one Steve was just looking at in number 2. And the reason we created this file is that type of question where you have what I'd call a kind of a graphically presented derivative that's very simple geometrically. And by geometrically, I mean, it's either piecewise linear, it might have a quarter circle or half circle piece thrown in. Steve had one that this one was a little bit of a variation. I actually had part of a parabola as part of the graph, that number 1 that Steve was looking at. But what we have here is in this top graph where you see the grid, this is my function f. Okay. And the function g is defined as a definite integral of that function that you can see, the piecewise linear one. And its lower limit is a, which is a constant, and we haven't specified what a is, just like it was in number 2, it wasn't really specified. And the variable is the upper limit of integration. And so that's going to be the value of g of x. So for example, we have one specific value of g that we can figure out that's kind of displayed by this shaded area here. So the integral under the red graph, which is f, from a, which is currently at 1, over to x equal 3 is, well, it looks like it's an area of positive 1.5 as we move from left to right. And so here on the graph of g of x, you can see when over here at x equal 3, we have a y value of 1.5. And if we change x, if we move x around, we're moving along the graph of g. If I move x to be the same as a, of course, it's going to be 0 area. Okay, so that's going to be a root from g. And if I start moving x to the left of a, and my red graph here is above the x-axis, that's actually going to be counting as a negative for the purposes of that definite integral. Now, here's what's kind of cool is what's going to happen if I change a? Well, let's see. I'm not going to change the red graph at all. All I'm going to do is change that lower limit of integration constant. And I'm still going to be considering this as a function of the upper limit. So what will happen to this graph here of my g function if I change a? So think about that a bit. And then I'm going to go ahead and try it out and see what happens. Okay, so I'm going to start changing a. And you see the entire graph is moving down. If I move a the other direction, graph is moving up. And so this changing of the lower limit, oh, that's heading down again. Interesting. So changing that lower limit,
Tom.
Yeah, that lower limit of integration is actually affecting a vertical shift of the antiderivative function, which is what that definite integral function is. And if we think of it, I joke around with Steve and Curtis that I call these kind of my duh aha moments, or I should say aha duh, is like, oh wow, that's really interesting. And it's like, well, duh, now I understand why. Is these definite integral functions, wherever we put a, the derivative of that function is the same. It's this red graph. And two antiderivatives of the same derivative can only differ by a constant. And so it has to be a vertical shift. That's the only change we could possibly have, is to shift the whole graph up and down. So it's kind of cool. And these are really rich questions. This particular file, by the way, you can just change the entire graph of your piecewise linear on the fly, which is kind of cool.
Yeah.
So it's actually lets you do a whole variety of these piecewise linear graphs and asks questions all along the same lines that Steve just discussed. So for example, if this is the graph of my derivative, where would there be a relative maximum? Where would there be a relative minimum, if any? Where would there be an inflection point? Things like that. Where's the antiderivative graph, concave up, concave down? So it's really rich file and very cool for illustration. All right, I will stop sharing and turn it back over to Steve now.
Okay, thanks, Tom.
Tom, as Steve is getting ready to share, is that file one that is on Math-Nspired, or is that one that you built and we can share with people otherwise?
It is on Math-Nspired in Calculus-Inspired. It may be one that, Steve and I are actually kind of looking at these files and revising them. That one, we might update it, refresh it a bit, but yeah, it's there and available for download. If people would like to get it and use it.
Okay.
All right, here's an interesting question, Curtis, and in the interest of time, we'll certainly post this answer. But this was on the Facebook page, and part of this certainly involves the AP Calculus curriculum, but there's also another part of this that involves trigonometric substitution, which I don't think is tested on the exam. But this was just a cool problem, and I had to put this on here. There were a couple of comments about this, but I didn't see a complete answer on the Facebook page, so I thought we should do this one. I'll just make one comment here up to this point, okay? Let's just find the integral of x, arctan x, divided by 1 plus x squared, that whole thing squared. How do you attack this one? So I sort of have in my mind a strategy of integration. What techniques would I use? And this seems like it might be a good candidate to start out with integration by parts. And the reason is because I can see that if I couple this x with the denominator, I can see that I have the derivative of that inner function, except for a constant. And I know that if I choose right in integration by parts, if I let u be equal to arctan x, then I know the derivative is 1 divided by 1 plus x squared, and I know I get rid of that transcendental function. That's a good thing, I think. That's what I think about. So my first step here was integration by parts, and I'll just show you that I ended up here with this integral on the end, and now I felt like I was a little stuck. How do you tackle that one? 1 divided by 1 plus x squared, that whole thing squared. I don't have the derivative of that inner function hanging around anywhere in that integrand. And to solve this one, you need to do, I believe, a trigonometric substitution. And again, Curtis will post this one so that everyone can see how I did it. If I arrow down a little bit, here's my final answer. And one of the things that I like to do is to graph things just to sort of confirm that I got the right answer. And in fact, this expression right here in blue, my graph of little f is a graph of the integrand, and capital F is a graph of the antiderivative. And if I look at this and reason out, I think I'm okay. Capital F is always increasing. I can see that its derivative, little f, is always positive. I can see that capital F is sort of leveling off here. its slope is going to 0. I can see that down here, its derivative is getting closer to 0. So I felt pretty good, pretty confident about this solution. So that's a great question. Karen Martin Swift posted that one. I hope that answers hers. And again, we'll post this in detail tomorrow, okay? Now, 4 we can look at in a little bit more detail. This was kind of a neat limit problem. The limit as x goes to 1 of log x divided by x to the 4th minus 1 to the 1/2. So the square root of that. So here's the first thing I did here. And if you look closely, let's see, if you look closely, I've got a question mark here above this equal sign. You know, the limit of this expression, I can pass that limit sign sort of through that square root symbol only if this limit on the inside exists. So I've got to think about that a little bit and see if that limit exists. I take a look at the limit of the numerator as x goes to 1. The log of x, well, it's continuous there. The log of 1 is 0. As x goes to 1, I have another polynomial here. Just plug in direct substitution. That's 0. And so just as a reminder, if I'm going to use L'Hopital's rule, I want to show that both the limit of the numerator and the limit of the denominator are 0. In expressions like this, I would argue against using just sort of arrows, and definitely argue against writing something like equals 0 over 0. So now I'm working with just that sort of inner function, that inner limit. I take the derivative of the numerator right here, the derivative of the denominator, and this is an important step here that I always emphasize. Once I've taken the derivative of the numerator and the denominator, before you try to evaluate that limit, one should try to simplify the expression, the resulting expression, as much as possible. And so I think I've done that correctly. And the limit here is just 1/4. I'm almost done. So that inner limit exists. And so the limit of this overall expression here is just 1/4, or the square root of 1/4, which is 1/2. Now, you know me, Curtis, I'm not content here. I want to check that a little bit. So what I've tried to do is to draw a graph of this function in blue. There is an open hole here at x equal 1. 1 is not in the domain. And I put this up here, but did not answer this question. So that's kind of a question for the chat, if you'd like. Can you tell me what the domain of this function is? And as I stare at this graph, it certainly looks like as x gets closer and closer to 1 from both the left and the right, it certainly appears that this function is getting closer and closer to 1/2. I feel pretty comfortable about that answer. Cool. I've got one more, Curtis, and I'm going to turn it over to Tom for some technology.
I think that's a good idea.
Tom and I have talked an awful lot about the solution to differential equations and slope fields. Lots of interesting things here. Tom and I had a great teacher in grad school, Shepley Ross, who was kind of the guru on differential equations, and we all wish he was still around so we could ask him some of these questions. But here's kind of a typical AP question. Is dy dx is equal to x sine x divided by y. It's an initial value problem. I know that y of 0 is equal to -1. I want to solve this problem. Lots of little things going on here. I skipped a couple of steps, but I'll add in a little bit more here. So the first thing I did here is I separate the variables. Get all the y's on one side, get all the x's on the other. Now I'm going to integrate both sides of this expression. On the left with respect to y squared over 2. On the right with respect to x. How do you integrate this expression? Well, it's not so simple. It's actually an integration by parts. I did not include those steps here, but it's a pretty straightforward integration by parts. And then I always recommend this at this point, before you try to solve for y. At this point, I would use this initial condition. So before you solve for y, I'm going to plug in, let's see, x equals 0 and y equal -1. And if I've done everything correctly there, c is equal to a 1/2. And now I've gone in this step and used the c equal to 1/2. And I think what I did here is I multiplied both sides of the expression by 2. And now a little tricky here at the end. I'm solving for y. I'm going to take the square root of both sides. But remember, we're looking for a function here. We're not looking for plus or minus a square root. And it turns out in this case that I want the minus square root of this expression. And the reason is because of the initial condition. At 0, y is equal to -1. Now, here's a little bit of support for all of this, and Tom will add a little bit more. Here's the slope field for this. So Tom is going to show you how to draw some slope fields with the 84 and maybe even the TI-Nspire. I've drawn this one with Mathematica, but I've also drawn in the solution curve, and there's some very interesting things going on here. So I would suggest and ask a couple of things, again, maybe for the chat window or maybe for you to think about with your students tomorrow. Look at this function, look at the graph of this solution function. It certainly has to go through 0, -1. But you'll notice that it stops right over here. And if you are following that slope field, you'd say, well, wait a minute. Why doesn't it cross the x-axis and kind of loop a little bit to the right there? But wait, it can't do that, because then it wouldn't be the graph of a function. So here's an interesting question. Can you find that value of x? Which leads me to, can you find the domain of this function y? Now, I didn't extend the slope field any farther out here to the right, but that's something that you might try with these calculator programs. Can you draw this complete sort of solution curve out to the right? Where does it stop there? Does it stop right here at x = 4? Boy, I don't think so. It kind of looks like if I'm following this slope field, and maybe it goes back around like this and stops somewhere up here. I wonder if we can find that x value and therefore find the complete domain here for this solution curve, for this solution function. So there's some neat things going on here, and I'm going to turn it over to Tom for a little bit of technology, and maybe he can even draw this slope field. Tom?
Okay. All right.
Here you go.
So I'm going to go ahead and switch over to the 84.
Okay.
And let me see if I'm successful and
got it.
Screen there. And that's coming up all right in your guys' view.
Yeah.
You can see that I've already got in the y equals menu on the 84 the solution that Steve came up with for his differential equation. There's that y2 is that negative square root of 1 minus 2x cosine x plus 2 sine x. Now, the TI-84 doesn't come with a built-in slope field plotter, but it turns out to not be a terribly difficult program to write, and we're going to make sure people have access to it. I've got a couple of slope field programs on this 84. Other people have written them. The idea behind a slope field's really super simple. If you have a derivative, if you have an expression for the derivative, you just evaluate it at a lattice of points, and whatever value it gives you, the derivative, well, you know that you interpret it as a slope, and you draw in a little tiny line segment with that slope at that point, centered at that point. So that's what we've got here. So in my program menu, you're going to see here a couple of slope field programs. One says SLP, FLD, and one is 2. They're almost identical. One just has kind of a finer resolution than the other. Okay. And I'll show you how these work. Both of these slope field programs, they expect to find your derivative expression in y1. So I'm going to go to y1 and put in the expression that was given in the problem that Steve was looking at. I believe that was x times the sine of x.
Right. Right.
And then that was all divided by y.
Right.
And this is where things look really, really strange. If you're used to the 84, you said, "Why I would never put a y in my y equals menu." But remember, this is just a placeholder for our derivative expression. So I'm going to just do an alpha y here. So I'm not going to try to graph y1. What that is, that's where my slope field program will look for my derivative. Okay. So now that we have that entered, I'm going to go to my program menu.
Tom, do you want that to be highlighted and turned on by having the enter or having the equal sign highlighted, or do you want to go ahead and turn that on?
Doesn't matter. The slope field program kind of takes care of that.
Oh, it does. Okay.
Yeah.
I just was thinking about ahead of time trying to figure that. Okay.
All right. So I'm going to go ahead and run the slope field program. And there it is. And what it's done is just taken that expression, and at each of these lattice points, it's evaluated for that x and y, what was the derivative value, and then put a line with that slope, a little piece of a line with that slope there. Now, this one is fairly crude. It's not nearly as fine as the one that Steve did with Mathematica. So I'm going to go ahead and do a little bit finer one. That's going to be that slope field 2. Let's just take a look at it. And it's just, it works exactly the same way. It just has a finer lattice. Oh, you know what I should have done is clear the screen first.
You can hit on to break the program if you want.
Yeah, let's do that. Okay. So let's go
to draw and clear draw.
Clear. That do it?
No, go to draw, second draw.
Okay.
And
clear draw.
Clear draw. Mm-hmm.
Okay, let's try that again. So that's my bad there. All right.
No, but that's a good way. That's a good thing for all of us to know how to clear a drawing on the screen.
Okay, this takes a little bit longer. I think that's the reason for the more coarse slope field program. Just runs faster, is less line segment. But this is one that's looking very, very similar to the one that Steve got with Mathematica.
Yep.
And if you go to your y equals menu, you can then plot a function on top of it. So if you came up with a solution working with separation of variables and you wanted to see, did it make sense, you could plot that on top of your slope field. Now, what's interesting here is Steve's slope field only extended from -4 to 4 in the x. My slope field actually extends a bit further. So we're going to have a chance to see when I graph this, what was Steve talking about. So let's graph his solution. Oh. Now, Steve was talking about this piece over here extending and stopping, but if you look over here, here's a whole other piece that's appeared that we didn't even see in Steve's drawing. But if we look at it, it looks like it's following the slope field very nicely. And you may want to think about what in the world is going on. By the way, I mean, this just does a really wonderful job of following that slope field.
Really.
I mean, it's not proof we have the solution, but visually we're like feeling really confident, right? We're just saying, well, this seems like it's making sense. If I look at my y equals and look at that solution, that cosine and sine, oh man, those are periodic functions. I think they're going to cycle through some values over and over again. So my guess is if we had a really large x-axis window, we would see several pieces repeating or something like that. It would be something going. Actually, this x thrown in here is going to do some different stuff. So it's going to have a really, really interesting domain is what I'm thinking. So but our cosine x and sine x are varying between -1 and 1. So that's the slope field program. Now on the TI-Nspire, you've got a built-in differential equation plotter. So you just enter your differential equation there, and it works just the same. So, now I did want to, as we're closing up, is just point out something to folks that I'm not sure if they realized or not. Is when you're so Steve came up with an explicit function. I wanted to talk about implicit graphing, where you're graphing relations. And you can actually use slope fields in an interesting way to do implicit graphing. Let me talk a little bit about that. So for example, let's say I had no clue what the graph of x squared plus y squared equals 9 looks like. Now, I'm expecting most all of you are saying, well, duh, that's just a circle, right? X squared plus y squared is going to be a circle of radius 3 centered at the origin. Well, let's say I didn't have any idea what that was, but I did know how to do implicit differentiation. Well, if you do it, that's probably one of the first examples you do in implicit differentiation is something like a circle. And if you do implicit differentiation on the circle, you end up with the derivative is negative x over y, I believe. Okay. So I'm going to put in for y1, oops, that's the wrong negative. Let's do negative x divided by y. And then I'm going to actually then run my slope field program with that as my derivative.
You're going to get a really strange graph that's going to graph on there still.
Oh,
well,
yeah.
I'm not sure.
You got to clear everything? No?
It clears.
Oh, it does. It turns them off.
Clear.
Okay.
Yeah.
Wow, that's cool.
So this is the slope field for the derivative differential equation dy dx equals negative x over y. Well, my original equation, x squared plus y squared equals 9, is supposed to be a solution. And so it's supposed to fit this slope field. And sure enough, what we see is what the slope field looks like. Ripples, throw a pebble in a pond. You see these concentric circles. It actually is generating lots of other curves, but they're all circles centered at the origin. In fact, anything of the form x squared plus y squared equals c is going to have the same derivative implicitly. And so we can really see that. And so this is kind of a poor person's way to come up with a contour plot or implicit plot, or if you have a slope field program. And I think that's we're probably about running out of time. So I'll stop share, turn it back over to you guys. And
well, fantastic. Tom, Steve, that's really cool. And I just want to put out a couple of things, actually, that we want to wrap up with. First of all, Tom, you're going to send me those files, those TI-84 files. So along with the presentation that Steve sends me tomorrow, and we'll post in that bulletin board link that we put in the chat just a little while ago. We'll put that back in the chat here real quick. We will also post at that same location in a zip file those TI-84 programs. So you can use those, download those, and send them over to your 84 calculators and use those slope field programs to generate a slope field on your 84s. The nice thing is you can do a slope field on the Nspire without a program, which is kind of cool. So there's an option for that. We didn't have time tonight to go into it, but that is something that you could do. Secondly, I want to bring up the idea that for all of you that are watching these either by live, or if you've tuned in later and watched the recording on demand from our YouTube playlist, you can email me at curtis@ti.com, and I will send you a link to generate a professional development hours certificate. So you'll be able to generate some credit for having watched this session through. So just email me at curtis@ti.com, and I'll respond with a way to generate that. Finally, I'm sure that all of you are waiting with bated breath to know who is our first giveaway person who's gonna grab a chance to have Steve and Tom teach a course or a session in their with their students remotely. And so tonight, Wanda Burns, you have been our recipient this evening for the giveaway. So Wanda, congratulations on that. You can email me directly, Wanda, curtis@ti.com, and we'll figure out a way to get that set up. For the rest of you who are watching this on demand, or if you're still watching live, you can tune in to the next session. We'll be back live at 8 p.m. Eastern on February the 21st. At 8 p.m. Eastern time, we'll be doing this again, and we will have another drawing that evening for another recipient to have their classroom taught by Steve and Tom. And I again want to reiterate that will be remotely. They're not going to be showing up in person in your classrooms, but rather we'll figure out a way for you to have them work with your students in a remote situation. So Wanda, congratulations. Super excited for you, and just make sure that you reach out to me and we'll work on getting that set up. All right, until next time, thank you very much, Steve, Tom, and Allison. Thank you so much for hosting this evening, managing the chat, and keeping us all on time. We'll talk to you guys in about a month.
All right. Thanks, everybody.